Two European countries just quietly fired the starting gun on a race almost nobody outside the physics world has noticed yet. And the winner could decide who controls the most powerful computing technology of the next century before most governments even finish writing their first strategy paper. While the United States and China dominate every headline about quantum computing, Spain and Germany have spent the last several months pouring billions of euros, building actual physical machines, and racing to install hardware inside real data centers, not someday, not in a decade, but right now in 2026. One of them just switched on a fully homegrown quantum computer built entirely with domestic technology. The other just launched a multi-million euro national competition specifically designed to produce error-corrected quantum machines that can compete with the best in the world. So who's actually winning this fight, and does it even matter who crosses the finish line first? Let's break down exactly what each country has built, what they're spending, and where this entire race inside Europe is actually headed. Start with Germany, because on paper, the numbers alone make it look like the heavyweight in this matchup. The German government has committed a staggering 2 billion euros to its national quantum strategy, anchoring an effort specifically designed to establish the country as a genuine quantum-o. The breadth of Germany's quantum ecosystem extends well beyond Munich alone, which is part of what makes the country's overall position genuinely formidable, rather than just concentrated around one lucky city. Across the wider country, researchers track somewhere around 86 distinct quantum-focused organizations, spanning hardware manufacturers, software developers, specialized cryogenic suppliers, and enterprise application companies looking to commercialize whatever quantum advantage eventually emerges. Berlin hosts a meaningful secondary cluster of its own, while smaller specialized hubs have emerged in Stuttgart, Siegen, and Braunschweig, the latter two becoming particular strongholds for trapped ion quantum computing approaches through companies like Elecutron and Qdora. A Munich-based company called PlanQC has separately built one of the largest neutral atom quantum systems anywhere in the country, operating a 256-qubit machine out of nearby Garching. Beyond pure hardware, Germany has also attracted significant venture capital, specifically targeting quantum computing, including a Munich-based deep tech fund, managing roughly 450 million euros in assets with direct investments into companies like IQM. The German Aerospace Center has separately built out its own dedicated quantum programs focused specifically on aerospace applications, satellite communications, and quantum sensing for Earth observation, adding yet another specialized vertical to the country's already broad quantum footprint. The most concrete proof that Germany isn't just talking about quantum computing, but actually building it, arrived in February 2026 when a machine called EuroQ-Exa went live. At the Leibniz Supercomputing Center just outside Munich, this wasn't a research prototype sitting isolated in a lab somewhere. EuroQ-Exa is a fully functioning 54-qubit superconducting quantum computer built on technology from Finnish company IQM, and it's directly wired into LRZ's existing classical supercomputer through what's described as a unified hybrid software environment. The launch itself was treated as a genuine national event rather than a quiet technical milestone, with the ceremony bringing together a European Commission Executive Vice President, Germany's own Parliamentary State Secretary for Research, the Bavarian State Minister for Science, and representatives from both LRZ and IQM, all gathered to mark what officials repeatedly described as the starting signal for Europe's journey into what they called unknown dimensions. That hybrid integration matters enormously because the near-term future of useful quantum computing almost certainly isn't quantum machines replacing classical supercomputers outright. It's the two working together, with quantum processors handling specific specialized calculations that classical chips genuinely struggle with, while the classical infrastructure handles everything else. Germany isn't stopping at 54 qubits either. A second, considerably more powerful system featuring more than 150 qubits is scheduled to join EuroQ-Exa by the end of this same year, which would represent close to a tripling of total processing capacity in under 12 months. IQM itself isn't treating Germany as its only major customer either, with a comparable 150-qubit machine also scheduled for delivery to Finland's VTT Research Center around the middle of 2026, underscoring just how much demand currently exists across the wider European quantum hardware market for exactly this kind of superconducting system. Germany backed up that hardware investment with an even more aggressive policy move in April 2026. The country's Federal Ministry for Research, Technology, and Space officially launched something called the Quantum Computing Competition, a deliberately structured funding contest aimed squarely at closing the gap between theoretical academic excellence, which Germany already has in abundance, and practical, deployable hardware, which is considerably harder to build. The stated target is concrete and specific: at least 2 new quantum computers operating at genuine European top-level performance by 2030, both fully error-corrected, which remains one of the single hardest unsolved engineering problems in the entire field. The application process itself was deliberately structured in two distinct stages, with interested companies and research consortiums first required to submit initial project outlines by mid-May, before a smaller shortlisted group moves forward to submit formal, detailed funding applications in a second round. Funding for individual projects or consortiums ranges from 20 to 55 million euros each, and crucially, the competition was designed to be deliberately technology agnostic, supporting three of the most promising hardware platforms currently being pursued worldwide: superconducting qubits, neutral atom systems, and trapped ion architectures. That breadth is a deliberate hedge against picking a single technological winner too early, given that the entire global quantum industry still hasn't settled on which underlying hardware approach will ultimately prove most scalable. German Research Minister Dorothy Baer framed the stakes in blunt, competitive language, stating plainly that Germany needs to be at the international forefront for the sake of both economic competitiveness and genuine technological sovereignty, adding that the program represents a decisive step taken together with the country's own existing quantum companies, rather than something imposed from above by government alone. Now turn to Spain, which has taken a noticeably different path toward the same overall destination, and arguably reached one specific milestone before Germany managed. 2. Spain's national quantum strategy runs through 2030 and carries an overall price tag of roughly 808 million euros, a serious commitment by any measure, even though it sits well below Germany's headline 2 billion euro figure. But raw budget size doesn't tell the whole story here, because Spain has focused that investment with remarkable precision on a single flagship achievement: building Europe's first quantum computer, constructed entirely using domestic, homegrown European technology, with essentially nothing imported from outside the continent. That machine is called EuroQCS Spain, and it switched on in May 2026 at the Barcelona Supercomputing Center, becoming the third quantum milestone achieved at that facility, and instantly becoming one of the most symbolically important machines on the entire continent. Spain's quantum ambitions extend well beyond this single flagship machine, and the broader ecosystem surrounding it deserves real attention as well. Multiverse Computing, headquartered in Spain and widely regarded as one of the most active quantum software companies anywhere in Europe, has raised chip manufacturing itself, which was completed in Gothenburg, Sweden, still firmly inside Europe rather than relying on suppliers from the United States or Asia. The machine itself now sits inside a genuinely striking physical setting, the renovated Torre Girona Chapel, the same building that already houses Spain's flagship classical supercomputer, Mare Nostrum 5, making the Barcelona Supercomputing Center one of the very first facilities anywhere in the world to physically combine classical and quantum. There's also a meaningful technical distinction between what these two flagship machines are actually built to do, and it's worth understanding clearly, rather than treating both countries as racing toward an identical finish line. Germany's EuroQXA is what's called a digital, gate-based superconducting quantum computer, The same general architecture pursued by major American players like IBM and Google, designed for broad, general-purpose quantum algorithms across a wide range of potential applications. Spain's EuroQCS Spain takes a fundamentally different analog approach, operating specifically as a quantum annealer, a specialized type of machine particularly well-suited to solving complex optimization problems, the kind that show up constantly in logistics planning, financial portfolio management, and supply chain coordination. The underlying physics behind that analog approach relies on something called adiabatic evolution, where the system is slowly and carefully transformed from a simple, easy to with Spain's joining as a recent and particularly symbolic addition given its all-European technology stack. The remaining systems in this network reveal just how deliberately diversified Europe's overall quantum approach has become. France's machine, located in Bruyères-le-Châtel and named Lucy, takes yet another distinct technical path, using particles of light itself as qubits in what's called a photonic quantum computer, an approach that can So, given all of that context, who's actually winning the race between Spain and Germany specifically? The honest answer depends entirely on which specific metric you choose to prioritize, because both countries are legitimately ahead on different fronts simultaneously. If you're measuring by total financial commitment, sheer breadth of supporting infrastructure, or overall qubit count, once Munich's planned 150 qubit upgrade lands later this year, Germany is clearly ahead, and it isn't particularly close. The country's combination of Munich Quantum Valley's dense company ecosystem, its multi-billion euro national funding pipeline, and its newly launched quantum computing competition gives it That distinction matters more than it might initially sound, especially inside the broader geopolitical context driving this entire continental push in the first place. The European Union's stated goal isn't simply to own more quantum computers than rival regions, an arms race purely measured in qubit counts. It's specifically about reducing dependence on critical dual-use technology. Controlled by companies and governments outside the EU's own borders, the same broad sovereignty logic that has already shaped Europe's approach to semiconductor manufacturing, cloud infrastructure, and now, increasingly, quantum hardware as well. Measured through that particular lens, Spain's smaller, scrappier, fully homegrown achievement at the Barcelona Supercomputing Center arguably represents a more philosophically significant milestone than Germany's larger but partially imported flagship system, even though Germany's overall program still dwarfs Spain's in nearly every conventional measure of scale, funding, and raw processing capacity. It's also worth noting that Spain and Germany aren't racing in a vacuum even within Europe itself, since the United Kingdom earmarked for quantum computing procurement and scaling efforts, including a dedicated program inviting private companies to submit prototype development proposals. The UK's National Quantum Computing Center has already brought a fully operational 100-qubit system online, while a separate American company, IonQ, has established its own dedicated quantum innovation center at the University of Cambridge specifically to host a 256-qubit system. None of that diminishes what Spain or Germany have individually accomplished. But it's an important reminder that the real competitive pressure shaping this entire European quantum push isn't really Spain versus Germany in isolation. It's the continent as a whole racing against external spending coming from London, Washington, and Beijing simultaneously, which is precisely why EU officials keep emphasizing coordination between member states rather than encouraging pure head-to-head rivalry. What both countries clearly understand, and what makes this rivalry genuinely productive rather than wastefully duplicative, is that prize. Spain's optimization-focused analog machine and Germany's general-purpose digital system aren't really fighting over identical territory. They're each carving out a distinct, complementary piece of a much larger continental puzzle that Europeans, officials hope, will eventually let the entire bloc compete credibly against the considerably larger quantum investments coming out of both the United States and China. So if you're looking for one single clean, satisfying winner between Spain and Germany in this particular race, you're probably asking the wrong question, because the more interesting story here genuinely isn't a binary contest between two rival nations. It's a fast-moving and surprisingly well-coordinated continental sprint, where both legitimate frontrunners actually need each other's distinct strengths to succeed at the much larger goal both governments have explicitly signed on to, keeping Europe relevant and competitive in what's shaping up to be one of the single most consequential technology races of the coming decade, one where the eventual winner won't necessarily be decided by a single country's flag planted on a single machine, but by whether the continent as a whole manages to turn dozens of these scattered national investments into one functioning, don't miss what happens next as both of these national programs race toward their next major milestones.